Our universe hides a secret architecture just beneath the surface of reality. We are about to journey through 30 mind-bending theories that attempt to map this cosmic blueprint. You will discover how everything you know about space and time might be a projection, an illusion, or just one page in an infinite cosmic library. What if the Big Bang was not the beginning but just one event in an endless cycle? What if every black hole contains an entire cosmos? By the end, you will have a new framework for understanding the very fabric of existence. What part of the cosmos sparks your deepest curiosity? The first thread in this cosmic tapestry is perhaps the most literal. We begin with cosmic strings. These are not the threads of a grand tapestry, but hypothetical cracks in the fabric of spacetime itself. Think of the universe cooling from its initial, searingly hot state, much like a sheet of ice forming on a pond. As it cools and settles, cracks can appear. Cosmic strings are those cracks, but etched into the very structure of reality. They are theoretical one-dimensional defects, infinitely long and thinner than an atom, yet possessing immense density. A single inch of cosmic string could weigh more than a mountain. Their existence would fundamentally warp the space around them. A string passing through a room would not crush anything, but its immense gravity would act like a ghostly lens. Everything on one side would appear duplicated, a bizarre form of gravitational lensing creating a phantom copy of the world. Their role could be even more profound. In the early cosmos, these vibrating, whipping strings might have provided the tiny seeds of density, the gravitational wells that eventually drew in matter to form the very first galaxies and clusters we see today. The implications grow stranger still. If a cosmic string forms a loop, or if two strings cross, the distortions in spacetime could become so severe that they might create closed time-like curves. In simpler terms, they could theoretically open pathways to the past, acting as natural time machines woven into the architecture of the universe. While we have not yet detected one, the search continues for their unique signature etched across the sky, a search for the cracks in our cosmic foundation. These cosmic cracks hint at a universe built on a deeper, more fundamental level. That foundation might be even more bizarre than one-dimensional strings. It might not exist at all in the way we perceive it. This brings us to the holographic principle, a theory so radical it suggests our rich, three-dimensional reality is nothing more than a projection. The world you feel, the space you move through, the very depth of the cosmos, could all be an illusion encoded on a distant, two-dimensional surface. The origins of this mind-bending idea are found in the physics of black holes. When matter falls into a black hole, what happens to the information it contains, the unique arrangement of its particles? According to the rules of quantum mechanics, information can never be truly destroyed. Yet a black hole's event horizon seems to be a point of no return. This is the black hole information paradox, a fundamental conflict between two pillars of physics. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, which is a measure of its information content, is not proportional to its volume as you might expect. Instead, it is proportional to the surface area of its event horizon. It was as if all the data about what fell into the black hole was not stored within its vast interior, but was painted onto its two-dimensional surface. Later, Gerard T. Hooft and Leonard Susskind took this stunning clue and ran with it. They proposed that this was not just a property of black holes, but a fundamental principle of the universe. Perhaps all the information needed to describe our three-dimensional reality, every star, every planet, and every one of us, is actually stored on a remote two-dimensional boundary that surrounds us. Think of a credit card hologram. The flat, shiny sticker holds all the data necessary to project a three-dimensional image that you can tilt and view from different angles. In a similar, though vastly more complex way, our universe could be a cosmic hologram projected from the data encoded on the boundary of space. If this is true, it means that the fundamental building blocks of reality are not located within the space we see, but on its distant edges. The world is not what it seems. This resolves the information paradox because the data never actually falls into the black hole. It is smeared and stored on the surface, preserving it forever. The holographic principle forces us to question the very nature of existence, suggesting that the depth and volume we experience are emergent properties, a magnificent illusion generated by an unimaginably complex calculation happening at the edge of everything. If our reality is a holographic projection, where does that projection come from? The holographic principle suggests the data for our universe is stored on a distant boundary, but that just pushes the mystery one step further. To find the source, we must confront a possibility that stretches the concept of reality to its breaking point. The cosmos might not be a single entity, but one of countless others in an unimaginably vast multiverse. The simplest form of this idea is known as the Level 1 multiverse. It begins with a straightforward yet staggering premise. Our universe is infinite. The space beyond our cosmic horizon, the farthest light we can possibly see, does not simply end. It continues forever, filled with more galaxies, more stars, and more planets. In an infinite volume of space, with only a finite number of ways particles can arrange themselves, every possible configuration must occur, not just once, but an infinite number of times. This is not science fiction, but a direct consequence of probability applied to an endless cosmos. Imagine a deck of cards, shuffle it, and you get one specific order. But if you had an infinite number of decks and an infinite number of shuffles, every single possible order of cards would appear, and would appear again and again without end. Now scale that up to the entire universe. Somewhere far beyond the reach of our telescopes, there is a region of space where every particle is arranged exactly as it is here. A perfect copy of our entire observable universe exists. In that distant volume, there is a planet identical to Earth with a person identical to you reading these identical words. And this is not a singular event. Because space is infinite, there are not just a few copies, there are an infinite number of them. Every possible variation of your life that could exist within the laws of physics is playing out somewhere. Every choice you did not make, every chance encounter that went differently, is reality in another of these cosmic domains. This idea arises naturally from our best theory of the universe's origin, cosmic inflation. This theory posits that in the first fraction of a second after the Big Bang, space itself expanded at an unimaginable speed, smoothing and stretching the cosmos to its vast size. But many models suggest this inflation never truly stopped. It ended in our part of the cosmos, giving rise to our universe, but in other regions it continues eternally. This is eternal inflation, a never-ending process spawning bubble universes. Our entire cosmos is just one bubble in a frothing, infinite sea of spacetime, where new bubbles are constantly forming, each with its own unique properties. The philosophical implications are profound. It challenges our very sense of uniqueness. Are we special, or are we just one version of a pattern repeated endlessly across the void? It transforms the cosmos from a single stage into an infinite library of realities, each volume telling a slightly different story. But that cosmic library of infinite copies requires a very specific kind of universe, one where the fundamental laws of physics are identical everywhere. What if the rules themselves are not universal but merely local bylaws? This brings us to the next staggering level of the multiverse, the realm of bubble universes. The theory of cosmic inflation, which describes the universe's explosive initial growth, holds a strange secret. For inflation to stop and create a stable universe like our own, the energy field driving it must settle into a stable, low-energy state. But our current physics suggests this field could have many different stable states, like a vast landscape of valleys, each with a different altitude. Our universe exists in one such low-energy valley, with its specific set of physical constants that allow for atoms, planets, and life. Yet, the process of eternal inflation suggests that while the field collapsed into our valley here, in other regions of the primordial foam, it collapsed into different valleys entirely. Each of these collapses created a separate bubble universe, nucleating like a pocket of air in a vast, rising loaf of raisin bread. The dough represents the inflating space, expanding at an incredible rate. The raisins are the bubble universes. As the loaf expands, the raisins move apart from one another, each contained within its own pocket of stable, slower expanding space. Inside each bubble, the physics can be completely different. In one, the force of gravity might be 1 billion times stronger, instantly crushing any structure. In another, the nuclear forces might be too weak to bind protons and neutrons, preventing atoms from ever forming. We live in a bubble where the numbers, the constants of nature, are just right for our existence. This is the anthropic principle in action, a selection effect that explains why we observe a universe so finely tuned for life, because in the vast multiverse, only such bubbles can contain observers to ask the question. These bubbles are generally forever disconnected from our own. The space between them is inflating so fast that not even light can bridge the gap. We are isolated in our cosmic pocket. Yet there is a tantalizing possibility. In the early chaos, these nascent bubbles could have collided. If our universe collided with another in its first moments, the impact would have left an imprint, a bruise on the cosmic microwave background radiation, the afterglow of the Big Bang. Astronomers have searched for these strange asymmetries in the sky, a potential scar from a collision with a neighboring reality with entirely different laws. While no definitive evidence has been found, the search continues for a sign that our cosmos is not alone, but merely one chamber in an infinite, frothing cathedral of realities, each operating under its own unique and unchangeable rules. There is another way to populate the multiverse, one that does not require an inflating cosmos or distant bubbles, but instead unfolds from the smallest events happening right here, right now. This is the many worlds interpretation of quantum mechanics, and it proposes that our reality is constantly splitting. At the quantum level, particles exist in a blurry state of possibilities called a superposition. An electron is not here or there, but exists as a wave of probability, a cloud of potential locations. The classic puzzle is what happens when we observe it. The traditional view, the Copenhagen interpretation, says the wave function collapses and the particle picks a single, definite location. But the many worlds interpretation proposed by Hugh Everett in the 1950s offers a startling alternative. There is no collapse. Instead, every possible outcome of a quantum event actually occurs. The universe literally branches into multiple copies to accommodate each possibility. Imagine you are about to flip a coin. In our everyday experience, it lands either heads or tails. But in the many worlds view, the moment the coin is in the air, the universe splits. In one branch, you see it land heads. In another, completely separate branch, an identical version of you sees it land tails. Both outcomes are equally real, but the two versions of you are now forever separated, each living in a distinct and branching timeline. This solves the measurement problem by eliminating the need for a mysterious collapse. The wave function just keeps evolving, and we, as conscious observers, are simply riding along one branch of an ever-expanding, infinite tree of reality. The implications for identity are dizzying. With every breath you take, with every random quantum event in your brain, the universe is branching. There is a version of you who made that different choice years ago. There is a version who took a different route to work today. Every possible history and future is being written simultaneously across the sprawling multiverse. This even redefines probability. When we say a quantum event has a 50% chance of happening, it does not mean it might happen. It means that in exactly half of the newly created universes, it does happen. You are simply the version of yourself who experiences one particular branch. The cosmos becomes a tapestry of limitless what-ifs, not as hypotheticals but as concrete realities in their own right. It is a vision of existence where nothing is ever lost and every possibility is fulfilled. This branching of reality into countless parallel worlds still requires a stage, a fundamental substance from which all possibilities are built. But what if that ultimate foundation is not a substance at all, but pure abstraction? The mathematical universe hypothesis proposed by physicist Max Tegmark takes the multiverse to its final, most dizzying level. It asserts that all mathematically consistent structures not only can exist, but they must exist. Our cosmos, with its galaxies, forces, and conscious life, is not just described by mathematics. It is mathematics. It is one specific, incredibly complex mathematical object, and every other possible mathematical structure is just as real, constituting its own separate universe. Think of the number pi. It is an abstract concept, an infinite, non-repeating decimal. It does not exist in space and time, yet its properties are fixed and discoverable. Now consider a mathematical structure that describes the laws of physics for a universe with 5 spatial dimensions. According to this hypothesis, that structure is not merely a description. It is a universe. Somewhere, in the most complete sense of the word, a 5-dimensional cosmos exists because the equations for it are coherent. This transforms mathematics from a human-invented tool into the ultimate reality, a vast and timeless library of all possible forms. Our physical laws are simply the local bylaws of the particular mathematical structure we happen to inhabit. This idea, known as the Level 4 multiverse, includes every conceivable variation of reality. It contains the infinite copies of the Level 1 multiverse, the bubbling domains of the Level 2, and the branching timelines of the Level 3. They all become subsets of a single, overwhelming truth that every story that can be written in the language of mathematics is being told in a universe of its own. Why, then, do we perceive this particular mathematical structure with its 3 dimensions of space and 1 of time? The answer is again anthropic. Our conscious awareness can only emerge in structures complex enough to contain self-referential subsystems like our own brains. We find ourselves in this universe not because it is special, but because it is one of the rare mathematical structures that allows for the existence of entities that can ask why. The implications are staggering. It means that a universe governed by entirely different logical rules, one where 2 plus 2 does not equal 4, could be real, provided its internal logic is consistent. It suggests that the quest for a fundamental theory of physics is not a search for the laws that govern our universe, but a search for our own cosmic address within the infinite library of mathematics. We are not just reading the book of nature, we are living inside one of its countless, timeless pages. Yet this infinite library of mathematical realities may exist within a far grander architecture. Our universe might not be a standalone cosmos, but a single membrane, a 3-dimensional world floating within a higher dimensional space. This is the startling vision of brane cosmology. The word brane comes from membrane, and in this theory, our entire 4-dimensional spacetime, 3 of space and 1 of time, is just one such surface. This brane exists within a much larger and mostly inaccessible realm called the bulk. Think of our universe as a single, impossibly thin page in a colossal, multidimensional book. We are confined to the surface of that page, able to move left, right, forward, and back, but utterly unaware of the other pages stacked above and below us in the bulk. This framework emerges naturally from string theory, which requires extra spatial dimensions for its mathematical consistency. Why, then, do we only perceive 3 dimensions of space? The proposal is that all the forces and particles we know of, like electrons and photons, are themselves open strings whose endpoints are stuck to our brain. They are like ink on the page, unable to leave its surface. This is why our reality feels so thoroughly three-dimensional. We are made of stuff that cannot escape the brain we call home. Gravity, however, is different. In many brain world models, gravity is caused by closed loops of string, vibrations that are not pinned down. These gravitational loops can leak off our brain and propagate through the higher dimensional bulk. This simple idea could solve a long-standing mystery in physics: why gravity is so astonishingly weak compared to the other fundamental forces. The electric force between two electrons is a trillion times stronger than the gravitational pull between them. If gravity is free to spread out into the extra dimensions of the bulk, its influence would be diluted across a much greater volume. From our perspective, trapped on the brain, gravity would appear as only a faint shadow of its true strength, like hearing a loud concert from outside the stadium walls. You are only experiencing a tiny fraction of the sound waves. This model also offers a dramatic alternative to cosmic inflation for explaining the universe's uniformity. Instead of a rapid exponential expansion, our three-dimensional brain could have simply collided with another parallel brain floating in the bulk. That colossal collision would have flooded our universe with energy, heating it to a uniform temperature and creating the conditions we see in the cosmic microwave background. In this scenario, the Big Bang was not the beginning of space and time, but a violent, localized event within a much larger, eternal meta-universe. The search for evidence of this grander structure continues. If gravity truly leaks into the bulk, it might cause tiny deviations in its behavior over very short distances, or even produce miniature black holes in powerful particle colliders. Finding such a signature would be our first direct glimpse beyond the page of our own reality, revealing that we are not the entire story, but merely one surface in a vast multidimensional volume. That collision of brains offers a radical new origin story for our cosmos, one where the Big Bang was not a singular beginning but a violent rebirth. This is the ekpyrotic universe model. Ekpyrosis is an ancient Greek word for conflagration, a great fire, and it perfectly describes the immense energy released when two parallel worlds slam into each other. In this cyclic vision, our three-dimensional brain universe exists in an endless dance with another, separated by a tiny gap in the higher dimensional bulk. They are drawn together by a force, perhaps a spring-like tension in the hidden dimensions, until they collide. That impact is our Big Bang. It is not the creation of space and time from nothing, but a moment of intense heating and expansion within a pre-existing eternal framework. All the matter and energy that would form our stars and galaxies was generated in that fiery encounter. After the collision, the brains rebound, moving apart and allowing the universe we know to expand and cool. But the attraction remains, and over trillions of years, the cycle will repeat. The brains will draw together again for another collision, another cosmic rebirth in a cycle without beginning or end. This elegantly solves two of cosmology's great puzzles, the horizon problem and the flatness problem, without needing a period of rapid inflation. The horizon problem asks why the universe is so uniform. Regions on opposite sides of the sky have the same temperature, yet they were too far apart for light to have traveled between them, meaning they could never have been in contact to equalize. Inflation solves this by saying they were once close together before a super-fast expansion blew them apart. The ekpyrotic model offers a different solution. Before the brain collision, the entire volume of our three-dimensional universe was contracted into a much smaller, ultra-dense sheet. Every point was in contact with every other, allowing it to smooth itself out into a uniform state. The collision and subsequent expansion then simply stretched that pre-existing smoothness across the entire sky. The flatness problem is similarly resolved. The geometry of our universe is incredibly flat, meaning parallel lines stay parallel, and the fabric of space has almost no large-scale curvature. This requires a very precise balance of energy in the early universe. The cyclic nature of brane collisions naturally drives the universe toward this flat geometry over many, many cycles, like a ball bearing settling into the bottom of a bowl after being bounced around. So how could we ever test such a grand idea? The key might lie in the gravitational waves generated by the primordial collision itself. While cosmic inflation also predicts a background hum of gravitational waves, the signal from an ekpyrotic event would be distinctly different. The violent, shearing motion of two vast branes scraping past each other would not produce the same uniform, random pattern. Instead, it could create a much weaker and potentially more structured signal. Future space-based observatories designed to listen for these faint ripples in spacetime might one day tune into this specific frequency. Detecting it would be like finding the cosmic fingerprint of that long-ago collision, the echo of the blow that brought our reality into being. It would tell us that our universe is not a one-time event, but a single note in an endless, cyclic symphony of creation and destruction. While string theory weaves extra dimensions into reality, its great rival takes a completely different path. Loop quantum gravity asks a simpler, more radical question. What if space and time themselves are not smooth and continuous, but are made of tiny, indivisible pieces? This theory seeks to merge general relativity with quantum mechanics, not by adding hidden dimensions, but by quantizing the very fabric of spacetime. It proposes that space is not an empty stage, but a dynamic, woven structure. Imagine the cosmos as a vast piece of fabric. At a distance, it looks perfectly smooth and continuous. But bring a powerful magnifying glass up close, and you see the individual threads woven together in a complex mesh. Loop quantum gravity suggests that spacetime is exactly like that. The fundamental building blocks are not particles existing in space, but tiny, finite loops of gravitational field, one-dimensional threads of space itself. These loops link together, forming a network of relationships known as a spin network. This is the quantum description of space. When this network evolves over time, it creates a structure called a spin foam, a frothing, dynamic history of these changing connections. This solves one of the great conflicts in physics. In Einstein's general relativity, space is smooth and can be warped and curved. In quantum mechanics, everything is grainy and discrete. Loop quantum gravity bridges this gap by saying that space itself is grainy. It is woven from these finite loops which have a tiny but definite size at the Planck scale. This is an almost unimaginably small distance, a billion trillion times smaller than the nucleus of an atom. At this scale, you cannot divide space any further. You reach the fundamental pixel of reality. This granularity has profound consequences, especially for the most extreme objects in the universe, black holes, and for the very beginning of time. The theory rewrites the story of the Big Bang. In the standard model, the universe emerges from a singularity, a point of infinite density where the laws of physics break down. But if space is made of finite loops, it cannot be compressed to an infinitely small point. There is a smallest possible size. This means that as we rewind the cosmic clock, the universe gets denser and hotter, but instead of reaching a singularity, the quantum nature of spacetime creates a tremendous repulsive force. The collapse halts and reverses, the universe rebounds. The Big Bang was not the beginning, but the big bounce, a moment of transformation from a previous collapsing cosmos. Our entire universe could be the phoenix-like rebirth of a prior reality that contracted down to a tiny but finite size before springing back into a new expansion. This cyclic vision offers an elegant alternative to a single creation event, suggesting an endless, breathing rhythm of cosmic collapse and renewal. The echoes of that primordial bounce might even be detectable in the faint radiation that fills the sky, a permanent whisper of the universe that came before our own. Our search for reality's fundamental building blocks leads us to a universe built from geometry itself. causal dynamical triangulations offers a radically simple picture, constructing all of spacetime from tiny triangular pieces. Imagine you have a vast box of identical equilateral triangles. Your task is to glue their edges together, but you must follow a strict rule. Time is treated as a separate, distinct dimension from the start, creating a causal structure that prevents paradoxes. You begin by building a stack of these triangular sheets, each sheet representing a single moment in time. The connections within each sheet define the spatial geometry of the universe at that instant, while the connections between the sheets define how that geometry evolves, creating a history of spacetime. This is not a physical model you build with your hands, but a universe generated in a supercomputer. The program starts with a random, chaotic jumble of these triangular blocks, a churning quantum foam with no discernible order. This is the primordial state, a boiling sea of possibilities where time and space have no clear meaning. The magic happens when the computer applies the rules of the theory and sums over every possible way these triangles can connect, every possible history. Out of this apparent chaos, a remarkable structure emerges. A smooth, four-dimensional universe spontaneously crystallizes with 3 extended dimensions of space and 1 of time. It is as if you shook a bag of random puzzle pieces, only for them to fall into a perfectly coherent picture. This emergence of a classical, large-scale universe from a disordered quantum soup is the theory's greatest triumph. It suggests that the smooth, predictable spacetime we experience is not fundamental, but a collective effect, much like the smooth surface of a pond, emerges from the frantic motion of countless water molecules. Our reality is not a given. It is a phase of matter, a stable configuration that arises from the statistical averaging of an unimaginable number of tiny, geometric events. At the very smallest scales, spacetime remains a roiling, fractal foam. But as we zoom out, these wild fluctuations cancel each other out, leaving behind the calm, continuous stage upon which our cosmic story plays out. This computational approach provides a tangible glimpse into how our universe might have woven itself into existence from pure geometry, one tiny triangle at a time. These geometric building blocks are a beautiful simplification, but they are not the only path toward a final theory. The ultimate goal of physics is a single, elegant framework that explains every force and every particle under one roof. This is the dream of a theory of everything, and its leading candidate is known as M-theory. For decades, string theory promised such a unification, describing particles as tiny, vibrating strings. But a major problem emerged. There were not one, but 5 distinct versions of string theory, each with its own equations and quirks. Physicists were baffled. How could there be 5 unique theories of everything? The answer arrived in the 1990s when it was discovered that these 5 theories were not rivals at all. They were simply different perspectives, different facets of a single, deeper theory, one that exists in 11 dimensions. This mother of all theories was dubbed M-theory. The M is deliberately mysterious, standing for matrix, membrane, or even magic, depending on who you ask. Its central revelation was that the fundamental objects of the universe are not just one-dimensional strings. They are multidimensional membranes or branes existing in up to 11 dimensions. A point is a 0 brane, a string is a 1 brane, and a sheet is a 2 brane. M-theory allows for branes of various dimensions, all vibrating and interacting in a cosmos with 11 dimensions. From this grand, 11-dimensional perspective, the 5 string theories we knew simply appear as different approximations, different slices through a much richer reality. This is the true potential of a theory of everything, a single mathematical engine from which all of physics, from the gravity that bends starlight to the nuclear forces that power the sun, can be derived. The dream is that one equation could describe every interaction in the cosmos. Yet, this magnificent unity comes with a staggering price, a cosmic landscape of almost limitless possibilities. To connect this 11-dimensional theory to our 4-dimensional world, the extra 7 dimensions must be curled up or compactified into a fantastically complex tiny shape. The specific way these dimensions are folded determines the laws of physics in the resulting universe, the masses of particles, the strengths of forces, everything. And here lies the challenge. The number of possible ways to fold these dimensions is astronomically large. Estimates suggest there could be 10 to the power of 500 distinct configurations. This is the string landscape, a vast, perhaps infinite, collection of possible vacuum states, each corresponding to a universe with different physical laws. Our universe, with its specific constants, is just one tiny garden in this cosmic wilderness. This landscape offers one potential answer to the fine-tuning problem, why our laws are just right for life. In such a vast landscape, it is statistically inevitable that some universes will have the right conditions, and we, of course, find ourselves in one of them. But this very solution creates the greatest obstacle for M-theory. How can we ever test it? With so many possible configurations, how do we find the one that describes our specific world? Making a specific prediction that can be checked in a particle accelerator or telescope becomes a monumental task. The energy required to probe the strings and membranes directly is far beyond our reach, and the theory is so flexible it can accommodate almost any observation. The search for evidence is now a search for subtle clues, like the signatures of cosmic strings from the early universe, or specific patterns in the cosmic microwave background that could only be explained by a primordial brain collision. Finding such a fingerprint would be a monumental breakthrough, our first glimpse into the 11-dimensional architecture that may underpin all of reality. Until then, M-theory stands as the most profound and ambitious map we have of the cosmos, a magnificent, untested symphony waiting for its first note of confirmation. But what if the universe does not bounce or collide, but simply fades away and is reborn from its own ashes? This is the hauntingly beautiful vision of conformal cyclic cosmology proposed by the Nobel laureate Roger Penrose. It paints a picture of an endless sequence of cosmic eras, each one called an eon, stretching from a big bang to an infinitely expanding, empty future. In the standard cosmic story, this end state is a cold, dark, and lifeless void, a true finale. Penrose's radical insight was to see this not as an end but as a new beginning. He realized that as the universe expands forever and all matter eventually decays, the distinction between space and time mathematically vanishes. In this state of pure, featureless emptiness, the universe loses all sense of scale. An infinite expanse becomes indistinguishable from a single point. Through a mathematical transformation known as conformal rescaling, the infinite, timeless future of one eon can be seamlessly stitched to the high-energy, zero-size beginning of the next. The end becomes the beginning. Imagine a vast, silent ocean that has stretched on for eons. All its waves have settled, and its surface is perfectly smooth and flat, stretching to every horizon. Now imagine that this endless, calm ocean can be mathematically remapped, its infinite expanse refocused into a single, hyper-energetic droplet. That droplet is the Big Bang of the next eon. There is no big crunch, no violent collision, just a smooth, geometric transition from one cosmic story to the next. The most startling claim for this theory lies in the sky itself. Penrose and his collaborators argue that the cosmic microwave background, the remnant heat from our own Big Bang, contains faint imprints from the eon that came before ours. These are called Hawking points, named after Stephen Hawking. In the previous eon, supermassive black holes would have slowly evaporated over unimaginable timescales due to Hawking radiation. The final, explosive burst of energy from one of these evaporations would have left a circular imprint of slightly higher temperature on the cosmic microwave background of our own eon. Finding these faint circles in the sky would be like finding a fossil from a previous universe. While this claim is highly controversial and debated among cosmologists, the evidence, if confirmed, would be profound. It would mean that the cosmic microwave background is not just a baby picture of our universe, but a palimpsest, a canvas on which the final moments of a long-dead cosmos are faintly written. Our entire existence would be just one chapter in an infinite cyclic epic, where each universe inherits a ghostly signature from its ancestor. Could the universe be running on hardware? The simulation hypothesis is one of the most provocative ideas in modern thought, suggesting that everything we perceive, from the farthest galaxy to the feeling of warmth on your skin, is part of an incredibly advanced computational model. This is not a new idea from science fiction, but a serious philosophical argument famously formalized by Nick Bostrom. His trilemma, known as the simulation argument, presents three possibilities, at least one of which must be true. First, almost all civilizations at our level of technological development go extinct before they can reach a post-human stage capable of running ancestor simulations. Second, any civilization that does reach that stage has no interest in running such simulations. Or third, we are almost certainly living in a simulation right now. The logic is stark. If even a tiny fraction of advanced civilizations run a large number of high-fidelity simulations of their own history, then the number of simulated minds would vastly outnumber the base reality minds. Therefore, if such simulations are possible and occur, the statistical probability that we are among the original biological beings is infinitesimally small. We would be the digital ancestors, not the flesh and blood ones. This leads to a strange form of cosmic imposter syndrome. If this is true, then the laws of physics are not fundamental truths, but the programmed rules of the simulation. This opens the door to a fascinating line of inquiry. Could we find evidence of the code? Just as a complex video game might use shortcuts to render distant objects or simplify calculations to save processing power, our universe might exhibit similar optimizations. Physicists have speculated that we might find these computational shortcuts in the fabric of reality itself. One place to look is in the behavior of high-energy cosmic rays. These are particles from deep space that strike our atmosphere with immense energy. The universe has a built-in speed limit, the speed of light, and a fundamental resolution, the Planck length. In a simulated universe, the physics engine would need to calculate the interactions of every particle, but doing so with infinite precision would require infinite processing power. A practical simulation would have to round things off to quantize space and time into a finite grid. At extremely high energies, cosmic rays might reveal this pixelation. If space is a discrete lattice, then particles traveling at different angles would experience it slightly differently, much like a low-resolution screen makes diagonal lines look jagged. We have not found such an effect, but the search continues for any anomaly in particle behavior that betrays an underlying architecture. Another potential glitch could be found in the fundamental constants of nature. Why is the speed of light exactly 299,792,458 meters per second? In a simulated reality, these numbers might not be profound truths, but simply the default parameters set by the programmer, or even the result of a mathematical bug that was too difficult to fix without crashing the entire system. The simulation hypothesis reframes our entire existence. The quest for a theory of everything becomes a search for the source code. A black hole might not be a gravitational singularity, but a data compression routine or a garbage collection process. The eerie laws of quantum mechanics, with their probabilities and observer effects, could be the result of the simulation only rendering reality in detail when it is being observed, again to save on computational resources. It is a concept that dissolves the boundary between physics and metaphysics, challenging us to consider that the greatest mystery of the cosmos is not its origin, but its developer. This statistical selection effect is known as the weak anthropic principle. We do not observe a universe with random properties, but one uniquely suited for our existence. The very fact that we are here to measure the cosmos acts as a filter. We could not possibly find ourselves in a universe where the nuclear force is too weak to form carbon, or where gravity is so strong that stars burn out in 1,000,000 years. The weak principle is a statement about our location within a wider cosmos, a necessary condition for observers. The strong anthropic principle takes a far more provocative stance. It argues that the universe must have properties that allow life to arise. This is not just a statement about our lucky position, but a suggestion of a deeper law or mechanism that compels the cosmos to be bio-friendly. Some interpretations of this strong version edge toward teleology, the idea that the universe has a purpose, that consciousness is not a random byproduct but a fundamental goal of cosmic evolution. Critics often dismiss the anthropic principle as a tautology, a circular argument that says we exist because we exist. But its true power is not as an explanation in itself, but as a critical lens for evaluating scientific theories. A theory that predicts a universe completely hostile to life can be ruled out, not because it is mathematically wrong, but because it is observationally self-defeating. We are here, so the theory must be incomplete. This logic finds its most potent application in the context of the multiverse. The staggering fine-tuning of our universe's constants becomes far less mysterious if ours is just one among a vast landscape of possibilities. In an infinite multiverse, every possible set of physical laws is realized somewhere. Most of those universes are barren, empty, or fleeting. We inevitably find ourselves in one of the rare gems where the numbers align to forge atoms, stars, planets, and eventually, beings who can ponder the stars. The anthropic principle becomes the selection bias that explains why our local environment seems so impossibly special. We are not at the center of the cosmos, but we are at the center of the subset of cosmos that can contain us. It answers the fine-tuning not with a designer, but with a cosmic lottery of unimaginable scale, where winning tickets, while incredibly rare, are guaranteed to be held by someone. Black holes may be more than cosmic graves, they could be cosmic wombs. The black hole cosmology theory proposes a breathtaking possibility that our entire universe is the interior of a black hole existing within a much larger parent universe. In this view, the Big Bang was not a singular beginning from nothing, but the violent birth of a new reality from the collapse of an object in another cosmos. The singularity at the heart of a black hole, a point where density becomes infinite and known physics breaks down, is reimagined. Instead of a dead end, it is a bridge, a transformational point where the laws of physics are reborn, creating the expanding spacetime we call home. This idea finds a strange resonance with the holographic principle. You may recall that the holographic principle suggests all the information within a volume of space is encoded on its two-dimensional boundary. A black hole's event horizon is exactly that kind of boundary. The information about everything that falls in is not lost but smeared across this surface. In the black hole cosmology, the event horizon of our parent black hole is not a distant wall. It is the edge of our observable universe, the cosmic microwave background radiation, the oldest light we can see, could be the translated image of that encoded information, the afterglow of our creation imprinted on the shell of our cosmic prison or our cradle. This leads to a truly fractal vision of reality. Every black hole that forms in our universe could, in turn, contain an entire cosmos within it. A star collapsing in our night sky does not vanish into nothingness, but pinches off a new space-time, spawning a universe with its own laws, stars, and potentially, its own black holes creating further generations. Our universe might be one branch on an infinite branching tree of realities, each nested inside the other. We look up at the dark, silent black holes in our galaxy and we see voids, but they may be teeming with entire histories, entire chains of causality completely disconnected from our own. The darkness is not an end but a horizon leading to a new beginning. This endless rhythm of cosmic rebirth finds its most elegant expression in the Big Bounce. While the ekpyrotic model relies on colliding branes, the Big Bounce emerges from the very fabric of spacetime, resisting its own destruction. It is the universe refusing to die. In the classic Big Bang story, rewinding time leads to a singularity, a point of infinite density where physics itself breaks down. But what if that singularity is not a final wall but a gateway? Theories like loop quantum gravity provide the key by revealing that space itself cannot be infinitely divided. It is woven from a fabric of finite, one-dimensional loops. Picture a spring being compressed. You can push it down, but eventually it pushes back with tremendous force. In the cosmic collapse of a universe, gravity is the force pulling the spring down. But as space is compressed to its smallest possible size, the quantum nature of these spacetime loops creates an overwhelming repulsive force. The collapse halts. And then it reverses. The universe rebounds in a great cosmic bounce, a Big Bang born not from nothing, but from the transformation of a previous cosmos. This is not a violent collision with an external object, but an internal metamorphosis, a phoenix rising from its own ashes. So what would such a bounce actually look like from the inside? In the final moments of the contraction, the universe would not be a cold, empty place. It would be heating up dramatically as all matter and energy are squeezed into an ever smaller volume. The cosmic background radiation, now a faint whisper, would become a blazing heat. Galaxies would merge, stars would be torn apart, and eventually, even atoms would be disassembled into a searing, dense plasma. But just at the point of maximum compression, the quantum repulsion kicks in. The universe does not reach a state of infinite anything. It reaches a minimum size and then explodes outward, initiating a new period of expansion and cooling. This leads to one of the most profound questions in all of physics. What happens to information across these cycles? In our universe, information seems to be preserved. The unique configuration of particles that makes you is, in principle, traceable through time. But if the universe is scrunched down to a hot, dense state where all structure is erased, is that information lost, scrambled, or somehow preserved? Some models suggest that the bounce acts like a cosmic reset button, wiping the slate entirely clean. Each new cycle begins with a blank canvas, its physical laws and constants potentially reshuffled. In this view, our universe's history is utterly unique and will leave no trace for the next. Other, more tantalizing models propose that information can survive the transition, perhaps imprinted onto the very quantum structure of spacetime itself. If this is true, then the universe that emerges from the bounce might carry faint, encoded echoes of its ancestor. The cosmic microwave background could hold not just the secrets of our own Big Bang, but ghostly patterns from a universe that existed trillions of years before our own. We would be living in a universe with a hidden, inherited memory, a story written in the language of physics, passed down through an endless line of cosmic generations. There is a ghost in the map of the universe, a mysterious alignment that seems to single out our own cosmic neighborhood. This is the axis of evil, a name that reflects just how deeply it disturbs our understanding of the cosmos. It all begins with the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky. This ancient light is remarkably uniform, a nearly perfect blackbody with only tiny, random fluctuations, the seeds from which all galaxies grew. According to the bedrock cosmological principle, the universe should have no center and no edge. It should look the same in every direction, with no preferred axis or special location. Yet, when scientists created a full sky map of this radiation, they found something unsettling. The largest scale fluctuations, the biggest hot and cold spots, are not randomly scattered. They appear to be aligned in a specific way, and that alignment eerily correlates with the plane of our solar system and the direction of our galaxy's motion. It is as if the universe's oldest fossil has our own address written across it. This is profoundly unexpected. Why would the most ancient structure in the cosmos, imprinted billions of years before our solar system even existed, seem to care about our local cosmic geography? The most conservative explanation is that this is a colossal statistical fluke. With any large set of data, strange patterns can appear by pure chance. Perhaps we are simply the unlucky observers who see a meaningless alignment, much like seeing a face in the clouds. Another possibility is that the signal is not primordial at all, but a foreground contaminant. Our view of the pristine cosmic microwave background is muddied by light from our own galaxy, dust and gas that must be meticulously subtracted. Could an error in this cleaning process have left behind a false pattern that just happens to line up with our solar system? The scientific community has rigorously investigated both of these possibilities, and the anomaly stubbornly persists. It has been confirmed by multiple independent satellites, each with increasingly sophisticated instruments, and the alignment remains a faint but persistent whisper against the cosmological principle. If it is real, the implications are staggering. It would mean the universe does have a preferred direction after all, a cosmic axis that breaks the fundamental rule of large-scale uniformity. This would force us to rewrite the textbooks. What could cause such a fundamental anisotropy? One radical proposal is that the fabric of spacetime itself might be twisted on a cosmic scale, like a vast, rotating structure that imprinted its spin onto the early universe. Another idea reaches back before the Big Bang, suggesting the universe inherited this preferred direction from a prior cosmic era, a fossil of a more complex geometry. The name Axis of Evil is not an exaggeration. It represents a direct challenge to the very foundation of modern cosmology, the idea that we do not occupy a special place. Finding that the universe has a spine and that we are curiously aligned with it would be one of the most humbling and revolutionary discoveries in the history of science, forcing us to see our cosmic home in an entirely new and unexpected light. This coherent stream of galaxies hints at a cosmos far larger than our observable horizon. Astronomers have detected a mysterious motion they call dark flow, a vast current where entire clusters of galaxies are drifting in a uniform direction at incredible speeds, millions of miles per hour. This is not the expected, random expansion of the universe, but a directed, collective movement, as if some immense, unseen force is pulling them. The source of this gravitational tug is not within our sight. It lies beyond the cosmic microwave background, beyond the farthest light we can see. Something with the mass of thousands of galaxies, a colossal concentration of matter, must be exerting its pull from a region of space that is causally disconnected from us, a place that light has not had time to reach since the beginning of the universe. This presents a profound puzzle. According to standard cosmology, the universe is homogeneous on the largest scales, and no such structure should exist beyond our horizon to create this flow. So what could possibly be out there? One of the most thrilling possibilities is that dark flow is our first indirect evidence for the multiverse. Remember, the bubble universes born from eternal inflation. Our cosmos is one bubble in an endless, frothing meta-universe. These bubbles are not infinitely far apart in a conventional sense, but they are separated by realms of inflating space that are expanding faster than light. While we can never visit them, gravity might be able to leak across the gap. The immense mass of a neighboring bubble universe, a cosmic island with its own entirely different laws, could be the gravitational anchor, the unseen attractor pulling on the galaxies in our own visible realm. It would be like feeling a steady ocean current, knowing it must be driven by a distant, unseen continent. The controversy around dark flow is intense, as some analyses of the data question the statistical significance of the signal. Yet if it is real, it paints a staggering picture. We are not just floating in an isolated cosmos. We are part of a vast archipelago of realities, and we can feel the tide from a neighboring island universe, a ghostly pull from a world we can never see, reminding us that our home is far grander and more connected than we ever dreamed. This fractal pattern in the cosmos suggests a universe built on repeating scales, a cosmic echo that never fades. The fractal universe hypothesis challenges one of the most sacred tenets of cosmology, the principle that on the largest scales, the universe is smooth and homogeneous. This idea proposes the opposite, that the distribution of matter is hierarchical, with clusters nesting within larger clusters, continuing endlessly. Galaxies form groups, those groups gather into colossal clusters, and those clusters themselves are part of immense superclusters, all arranged in a vast, sponge-like network of filaments and voids. The question is whether this pattern of clustering has a limit or if it truly continues forever. The roots of this idea stretch back over a century to the work of astronomer Carl Charlier. He constructed a model of a hierarchical universe to solve a paradox: why the night sky is dark. In an infinite, smooth universe filled with stars, every line of sight should eventually end on a star, making the entire night sky as bright as the surface of the sun. Charlier realized that if stars were grouped into galaxies, galaxies into clusters, and clusters into ever larger structures with ever-increasing gaps between them, then most lines of sight would end in empty space, gracefully explaining the darkness we see overhead. For decades, the cosmological principle held sway and the fractal idea was sidelined, but modern, massive galaxy surveys have forced a re-examination. When we map the positions of millions of galaxies, the fractal pattern is undeniable up to a certain point. The clustering is real and measurable. The great debate now is about the scale. Is there a maximum size, a transition point beyond which the universe finally becomes smooth and the clustering fades into a uniform haze? Some analyses of the data suggest this transition happens at around 300 million light-years. At scales larger than that, the universe may indeed begin to look homogeneous as the standard model requires. Yet other studies, looking at different surveys, argue the fractal pattern persists with no clear end in sight. This is not just an academic argument. If the universe is truly fractal on all scales, it would mean there is no average density of matter for the entire cosmos. The properties of the universe would depend on where you are, fundamentally undermining the foundation upon which our models of the Big Bang and cosmic expansion are built. We would have to redraw our map of reality from a uniform ocean to an endless, structured labyrinth with no center and no edge. The search for this ultimate transition scale continues, a quest to determine if the cosmic tapestry is woven with a repeating, infinite pattern, or if it finally smooths out into a featureless sea at the very grandest of scales. But what if the darkness of the cosmos conceals an entire sector of physics that operates without particles? This is the strange world of unparticle physics, a theory proposing a hidden realm that does not play by the familiar rules. In our standard model, everything is made of particles, quarks, electrons, photons, each with a definite mass and a specific place in the quantum zoo. Unparticle physics suggests there could be a completely separate sector, a hidden world of stuff that is not made of particles at all. Its behavior is governed by a principle called scale invariance. Imagine looking at a coastline from an airplane. You see its general shape. As you descend, you see more detail, bays and headlands. If you could zoom in infinitely, you would see the same level of intricate, repeating detail on every scale, from cliffs down to individual grains of sand. A scale invariant system looks the same no matter how much you magnify it. This is utterly unlike a particle. An electron always has the same mass, a fixed identity. But an unparticle field has no fixed mass or scale. It behaves like a continuous, fluid substance rather than a collection of discrete bits. So how could we ever detect such a ghostly presence? The key might be in the aftermath of violent particle collisions. Inside giant machines like the Large Hadron Collider, scientists smash protons together at nearly the speed of light and meticulously tally the energy and momentum of all the debris that flies out. According to the law of conservation of energy, the energy going into the collision must equal the energy coming out. Sometimes there is a deficit, a significant amount of energy that seems to have simply vanished. In conventional physics, this is a signature of dark matter or neutrinos, particles that interact so weakly they escape the detector unseen, but unparticles could produce an identical signal. If this hidden sector exists, the violent collisions in our particle accelerators could briefly create a bridge to it, allowing energy to leak into the unparticle realm. Since unparticles do not register in our particle detectors, they would carry that energy away, leaving behind a mysterious imbalance, a clear sign that something is missing. This missing energy could be the ghostly fingerprint of an entire hidden cosmos, a parallel physics operating right alongside our own. The implications reach far beyond the laboratory. This scale-invariant stuff could be a fundamental component of the universe's greatest mysteries, dark matter and dark energy. Its continuous, fluid-like nature could explain why dark matter seems to form a smooth halo around galaxies rather than clumping like ordinary matter. And because it is not tied to a specific scale, its influence could evolve over the lifetime of the cosmos, potentially contributing to the repulsive force we call dark energy. Unparticle physics offers a radical redrawing of reality's blueprint, suggesting that the solid, particulate world we know is just one layer of existence, floating atop a deeper, seamless, and profoundly strange hidden ocean. We are now forced to confront the very stage upon which the cosmic drama unfolds. Spacetime itself, the fundamental fabric of reality, might not be fundamental at all. It could be an illusion, a collective phenomenon that emerges from something far more basic, the ghostly quantum connections known as entanglement. This is the radical proposal of emergent spacetime, where the distance between two objects is not a primary property of the universe, but a consequence of how deeply their quantum information is intertwined. Think of a piece of cloth. From a distance, it appears as a smooth, continuous sheet. But up close, you see it is woven from countless individual threads. The cloth itself, its smoothness and its strength, is not a fundamental substance. It emerges from the intricate connections of those threads. In this new picture, space-time is the cloth and quantum entanglement is the thread. The more two particles are entangled, the more tightly woven their connection becomes, and the closer they are in the emergent fabric of space. If you could somehow sever the entanglement between them, the spatial connection would literally dissolve. They would not be far apart, they would cease to have a well-defined spatial relationship at all. This leads to one of the most profound conjectures in modern physics, known as ER equals EPR. It connects two ideas that were thought to be completely separate. On one side, you have ER, the Einstein-Rosen bridge, which is the formal name for a wormhole, a tunnel through spacetime. On the other side, you have EPR, named for Einstein, Podolsky, and Rosen, who first identified the spooky action at a distance of quantum entanglement. The conjecture boldly states that these are not two different things, but two descriptions of the same phenomenon. A wormhole, a tunnel in spacetime, is equivalent to a pair of entangled particles. When two black holes are entangled, a wormhole connects them. The spooky link that allows information to be shared instantly across vast distances is not a weird loophole. It is a literal shortcut through the geometry of space, a tiny stitch in the cosmic fabric. This completely reframes what entanglement is. It is not a force that acts across space, it is what creates the space in the first place. The entire universe could be seen as an impossibly complex and dense network of entanglement, a cosmic tapestry where every thread weaves a tiny piece of the spatial dimension we take for granted. The three-dimensional volume we move through is like the rich image on a computer screen, but the real processing, the real reality, is the tangled web of quantum connections running the code underneath. If this is true, then the Big Bang was not an explosion in space, but the moment when a vast, primordial state of entanglement began to crystallize, giving rise to the geometry of spacetime itself. We are living inside a web of quantum links, a cosmic tapestry still weaving itself into existence with every passing moment. This discrete tapestry of spacetime finds its purest mathematical form in causal set theory. It proposes that the deep structure of reality is not a smooth fabric, but a vast collection of discrete points, the atoms of spacetime themselves. These points are not scattered randomly. They are connected in a web of cause and effect, a partially ordered set where the only fundamental relation is which event can influence another. In this view, spacetime is not primary. Causality is. The entire cosmos is a vast, growing network of causal relationships, a cosmic ancestry chart where every point knows which other points it descended from. The smooth, four-dimensional continuum we experience, with its familiar distances and durations, is not the foundation. It is a large-scale illusion, an approximation that emerges from the sheer density of these causal connections. Think of a photograph in a newspaper. Up close, you see it is nothing but a grid of discrete black and white dots. Yet, from a normal viewing distance, those dots blend seamlessly into a continuous image with shapes, shadows, and depth. In causal set theory, our smooth spacetime is that photograph, and the individual dots are the causal atoms. The order of these dots, which one comes before another, creates the very arrow of time and the geometry of space. This elegant idea has a profound consequence. It naturally avoids the singularities that plague general relativity. In Einstein's theory, black holes contain a point of infinite density, and the Big Bang emerges from another, places where the mathematics breaks down and physics loses its meaning. But in a causal set, there are no infinite densities. The universe is composed of a finite, though astronomically large, number of these discrete elements. You can only pack so many causal atoms into a given volume. There is a fundamental limit, a smallest possible scale, which prevents the universe from ever collapsing to a true mathematical singularity. The Big Bang was not a point of infinite anything, but a moment of maximal, finite density, the beginning of our particular chain of causality. The challenge for the theory is to show exactly how our familiar, four-dimensional world, with its specific laws of physics, crystallizes from this abstract network of causal links. How does gravity emerge from the pattern of connections? The quest is to find the fundamental algorithm that takes a causal set as input and outputs the gentle curvature of spacetime, the force that guides the planets. It is a vision of a cosmos built not from substance but from relationship, a universe where the simple, austere logic of cause and effect is the ultimate foundation of all we see and feel. A perfect symmetry seems like it should lie at the heart of the cosmos, a fundamental even-handedness where the laws of physics do not care about left or right. Yet our universe possesses a strange and fundamental bias, a broken mirror. This is the mystery of parity violation in the weak nuclear force. In the realm of electromagnetism and gravity, the laws are perfectly symmetric. A reaction that works here would work exactly the same way in a mirror world. But the weak force responsible for nuclear decay is different. It has an absolute preference for left-handed particles. In a radioactive decay, the emitted electrons always spin in a specific direction, like a left-handed corkscrew. If you could watch this decay in a mirror, the reflected image would show a right-handed corkscrew, a process that simply does not occur in our reality. The mirror image is a lie. The universe on this fundamental level can tell its left from its right. This profound asymmetry has puzzled physicists for generations. Why would one of the core forces of nature break such a basic symmetry? One compelling solution is as elegant as it is staggering: the mirror universe hypothesis. It proposes that this broken symmetry is only an illusion from our limited perspective. The cosmos is actually perfectly symmetric, but we are only seeing one half of it. There is a mirror universe, a complete copy of our own, where the asymmetry is reversed. In that reality, the weak force prefers right-handed particles. Over there, what we call left is their right. This mirror world is not made of antimatter. It is a complete reality with its own planets, stars, and perhaps even life, all built from mirror matter. The two universes are woven together, perfect mirror images, restoring the cosmic balance. We are not aware of this twin reality because the two sectors interact with each other in only one way, through the faint whisper of gravity. The particles of their world are completely invisible to all our forces, and ours are invisible to theirs. They pass through us like ghosts, feeling only the gentle, universal tug of gravity. This leads to a breathtaking possibility. This mirror matter, utterly dark and unreachable to our telescopes and particle detectors, could be the mysterious dark matter that holds galaxies together. The missing 85% of the universe's mass might not be some exotic particle, but simply the stars and planets of our cosmic mirror image, forever hidden from our light. How could we ever hope to detect such a phantom reality? The most promising window is through the most ghostly particles we know, neutrinos. These elusive particles are already shape-shifters, oscillating between different types as they travel. If the mirror universe exists, our neutrinos might occasionally oscillate into their mirror neutrinos, vanishing completely from our detection. By carefully studying the flow of neutrinos from the Sun, nuclear reactors, and powerful particle accelerators, physicists are searching for this specific deficit, a telltale sign that some of them are slipping through the looking glass into the mirrored half of existence. Finding such a signal would be the ultimate proof that our universe's apparent flaw is the key to a far vaster and perfectly balanced cosmic duality. The very fabric of time might hold a secret rhythm, a ticking deep within matter itself. Time crystals are not science fiction. They are a bizarre new phase of matter that fundamentally challenges our understanding of equilibrium. All matter we encounter, from ice to steam, exists in a state of thermal equilibrium, meaning its atoms have settled into their lowest possible energy state. A time crystal shatters this rule. It is a quantum system in its ground state, yet it never settles down. It oscillates, repeating a pattern in time forever. Think of a perfectly still pond representing a normal crystal in equilibrium. Now imagine a single droplet in that pond that, without any external push, continues to ripple up and down on its own, never stopping. That droplet is a time crystal, a structure that breaks time translation symmetry. It does not just exist in space like a diamond, it performs a perpetual dance in time. For years, physicists argued such a thing was impossible, a quantum version of a perpetual motion machine. Then, researchers realized they could create these states within carefully controlled quantum systems, using periodic laser pulses to nudge a chain of ions or a dense lattice of spins into this strange, non-equilibrium order. The system does not absorb energy from the laser to heat up. Instead, it responds at a different, slower rhythm, locking into its own intrinsic beat. This is not perpetual motion in the classical sense, as no work is being extracted, but it is a form of perpetual change, a clock that ticks without being wound, powered by the quantum structure of its own ground state. The implications ripple outward, touching the nature of time itself. Could the universe contain natural time crystals, perhaps within the extreme conditions of neutron stars or as relics from the Big Bang? Their existence proves that matter can organize itself not just in space, but in the dimension of time, opening a new chapter in our search for exotic states that might define the hidden architecture of the cosmos. One of the most enduring mysteries is the nature of the invisible dark matter that holds galaxies together. An elegant solution proposes that it is not a new particle at all, but ancient cosmic fossils from the dawn of time, primordial black holes. These are not the stellar black holes formed from collapsing stars. They would have been forged in the extreme density and pressure fluctuations in the first second after the Big Bang, when the universe was a seething, chaotic soup. A patch of space just slightly denser than its surroundings could have collapsed directly under its own gravity, pinching off into a black hole of almost any size. For decades, this idea was largely ruled out, as too many of these black holes would disrupt the delicate processes of star formation and the cosmic microwave background. But recent observations have reopened the case, carving out specific mass windows where these ancient objects could still account for all the dark matter. One promising window is for black holes with masses similar to a large asteroid around the mass of the Moon. Another exists for much larger objects, tens of times the mass of our Sun. How could we possibly detect such dark, compact objects drifting through the galaxy? The primary method is through a phenomenon called gravitational microlensing. If a primordial black hole passes directly between us and a distant star, its gravity will act as a lens, bending the starlight and causing the star to temporarily brighten. The duration of this brightening flash tells us the mass of the invisible lens. Vast astronomical surveys are constantly monitoring millions of stars, searching for these telltale flashes that betray the passage of a dark, ancient wanderer. Another detection method comes from the ripples in spacetime itself. When two primordial black holes spiral into each other, they emit gravitational waves. The LIGO and Virgo observatories have detected many black hole mergers, and some of these collisions involve black holes in a mass range that is difficult to explain through standard stellar collapse. Could these be the mergers of primordial black holes, the dark matter itself clumping and colliding in the cosmic dark? Their influence could be even more profound. These primordial black holes, formed in the earliest moments, could have acted as the first gravitational seeds in the universe. They would have drawn in vast clouds of gas, accelerating the formation of the very first stars and galaxies. Some of them, by feasting on this primordial gas, could have grown to become the supermassive black holes that now lurk at the hearts of galaxies, including our own Milky Way. This theory weaves together three great cosmic puzzles: dark matter, the origin of supermassive black holes, and the rapid formation of early galaxies, into a single, compelling narrative. The dark matter halos enveloping galaxies may not be a diffuse cloud of unknown particles, but a swirling swarm of trillion of these primordial relics, the unseen architects of the cosmic structure we see today. The universe's hidden architecture might not require invisible matter at all, but a fundamental rewrite of gravity itself. For generations, we have understood the cosmos through the elegant equations of Newton and Einstein, where gravity dictates the dance of celestial bodies. But a stubborn anomaly refuses to fit this picture: the galaxy rotation problem. Stars at the outer edges of spiral galaxies orbit far too quickly. According to our established laws, these distant stars should be flung away into the void, their velocity insufficient to be held by the galaxy's visible mass. The prevailing solution has been to invent dark matter, an unseen substance providing the extra gravitational glue. Yet an alternative path dares to ask, what if our equations are simply incomplete? This is the radical proposal of modified Newtonian dynamics, or MND. It suggests that gravity behaves differently at extremely low accelerations, like those experienced in the far-flung outskirts of galaxies. In these cosmic hinterlands, the force of gravity would become slightly stronger than Newton's inverse square law predicts, just enough to keep those fast-moving stars in their orbits without any need for dark matter. Think of driving a car on a familiar road. At high speeds, your steering feels responsive and precise. But if you were to drive at a crawl across a vast, empty salt flat, the rules might feel different, the steering becoming disproportionately sensitive to the slightest turn. MND proposes a similar shift for gravity in the realm of the extremely faint. For individual galaxies, this tweak to the laws of physics works astonishingly well, matching the observed rotation curves with remarkable precision. The success of MUND, however, shines brightest on a single stage. When we zoom out to the scale of entire galaxy clusters or the cosmic web, the evidence for some form of unseen mass becomes overwhelming. The way these colossal structures bend light, a phenomenon known as gravitational lensing, reveals far more gravity than the visible matter or even MUND can easily explain. This has led to another, even more dramatic possibility, a fifth fundamental force. Beyond gravity, electromagnetism, and the strong and weak nuclear forces, there could be an unknown interaction that only manifests over vast astronomical distances. This hidden force would operate alongside gravity, subtly shaping the cosmos without the need for dark matter particles. Experiments are underway to hunt for the whisper of this fifth force. Scientists use exquisitely sensitive instruments to measure the gravitational attraction between objects at tiny, sub-millimeter distances, searching for any deviation from the expected pull that would betray a new kind of interaction. So far, no definitive signal has been found, leaving physics at a crossroads. Do we populate the universe with a mysterious, invisible substance that outweighs everything we see, or do we rewrite the fundamental laws that have guided our understanding for centuries? The choice defines our map of reality, a choice between finding new pieces to the cosmic puzzle or redrawing the puzzle's board itself. The ultimate statistical fluke might not be a universe but a single conscious mind. This is the unsettling paradox of the Boltzmann brain. It emerges from a simple, profound truth: systems tend toward disorder. A cup of hot coffee cools to room temperature, its heat dissipating into the air. This is the second law of thermodynamics, the relentless increase of entropy or randomness. Yet, in a truly eternal and infinite universe, even the most unlikely events must occur given enough time. Given an eternity, random fluctuations in the quantum void could, by pure chance, assemble a fully formed, self-aware brain, complete with false memories of a past that never existed. This brain would briefly flicker into consciousness, perhaps believing itself to be a person sitting and watching a video, only to be almost instantly dissolved back into the chaotic soup from which it came. The paradox lies in the statistics. For the universe to evolve a single, ordered planet like Earth, it had to start in an even more ordered state, an incredibly low entropy configuration like the Big Bang. This is an astronomically rare starting point, but in an infinite sea of time and chaos, it is far more likely for a random fluctuation to produce one self-aware brain, with its limited ordered memories, than to produce the entire, vast, and ordered cosmos we see around us. If our standard cosmological models point toward an eternal and infinite universe, then the statistical conclusion is bizarre and disturbing. You and I, and everything we perceive, should be far more likely to be one of these fleeting, disembodied Boltzmann brains than to be the products of a 14-billion-year cosmic evolution. This is not just a philosophical curiosity, it is a direct challenge to our most fundamental assumptions about reality. How can we trust our memories of a consistent past if they could be a random, momentary glitch? Cosmologists take this problem seriously because it acts as a litmus test for their models. Any theory that predicts an eternal universe or a universe with an eternal future must somehow explain why we are not Boltzmann brains. The primary argument used to resolve the paradox is an appeal to our observations. We clearly see evidence of a real, structured past, from the fossil record on Earth to the cosmic microwave background in the sky. Our universe is not in thermal equilibrium, it is still evolving from a low entropy beginning. Therefore, we can use our coherent observations to rule out the Boltzmann brain hypothesis for ourselves. We are not random fluctuations because a random fluctuation would not produce the rich, consistent history we observe. This is known as the past hypothesis, the idea that our universe began in a very special, low-entropy state, setting the arrow of time and making our ordered existence possible. The debate forces us to confront the very nature of existence in an infinite cosmos, questioning whether our sense of a continuous self is the rule or a breathtakingly rare exception in a sea of chaotic, temporary minds. Our universe may harbor exits as well as entrances. If a black hole is a cosmic one-way street, a place from which nothing can return, then its theoretical twin is the white hole, a place where nothing can ever enter. Picture a black hole in reverse. Instead of a relentless gravitational pull dragging everything inward past an event horizon, a white hole would violently expel matter and energy, spewing it out into the universe while forbidding any approach. The mathematics of general relativity allows for such a bizarre object, but its existence seems to defy the second law of thermodynamics, the universal trend toward disorder. How could something only give and never receive, forever increasing its own order? One compelling resolution is that a white hole is not a separate object but the other end of a black hole. In this view, the matter that falls into a black hole does not end at a singularity, but is shunted through a tunnel in spacetime and ejected from a white hole in another part of the cosmos, or even in another universe entirely. This cosmic pipeline is known as a wormhole. A wormhole is a shortcut, a bridge connecting two distant points in space and time. Imagine the universe is the surface of an apple. A worm digs a tunnel directly through the fruit's core, creating a path far shorter than the one along the curved skin. A wormhole does the same for space-time, offering a potential route for instantaneous travel across galactic distances or even into the past. The problem is stability. The kind of wormhole predicted by Einstein's equations would be incredibly fragile, pinching shut into a singularity in an instant, long before even a single photon could traverse it. To hold this tunnel open, you would need a form of exotic matter with negative energy density, a substance that creates a gravitational repulsion, propping the wormhole's throat open against its own crushing weight. While we have never observed such exotic matter, the strange quantum effects near a black hole's event horizon suggest that negative energy states might be possible, at least for brief moments. If a stable wormhole could be created or found, it would be the ultimate time machine. Because the two mouths of the wormhole are connected through a shortcut, their clocks could fall out of sync. If you were to take one mouth on a high-speed journey near the speed of light, time dilation would cause it to age slower than the stationary mouth. Upon returning, you would have a tunnel not just between two places, but between two times. Walking in one direction might send you to the future, while walking the other could lead you to the past. This introduces the classic paradoxes, like going back in time to prevent your own birth. The laws of physics might prevent such paradoxes through mechanisms we do not yet understand, perhaps by making the wormhole collapse the moment a paradox is about to occur. The search for these space-time shortcuts continues, not with spaceships but with mathematics, as we probe the deepest possibilities hidden within the fabric of reality. The stability of our universe rests on a knife's edge, held in place by the fragile energy of empty space itself. This vacuum is not a true nothingness, but a field seething with quantum potential. The unsettling possibility is that this vacuum is not in its most stable, lowest energy state. Instead, it might be metastable, like a ball resting in a small dip on the side of a vast, steep hill. It seems stable for now, but a nudge could send it rolling into the true abyss below. In our cosmos, that nudge could be a random quantum fluctuation, a tunneling event that spontaneously creates a tiny bubble of true vacuum. Inside this bubble, the laws of physics would be completely rewritten. The fundamental constants that allow atoms and molecules to exist would vanish. The bubble would then expand in all directions at the speed of light, a sphere of absolute oblivion. There would be no warning. One moment, the universe would be as it is. The next, an invisible wall of fundamental change would be upon you, and everything you know would simply cease to be in an instant. The trigger for this cosmic doom could have already happened somewhere in the vastness of space, and its wave of destruction could be on its way right now. The most chilling clue to this possibility comes from the Higgs boson. The mass of the Higgs particle discovered at the Large Hadron Collider is precisely in the range that suggests our vacuum is indeed metastable. It is not a guarantee, but a stark warning from the mathematics of the universe itself. This ultimate fate would not be a fiery crunch or a frozen silence, but a silent, instantaneous rewrite of reality itself, a final and absolute end to the cosmic story. It is a reminder that the stage upon which we exist may be temporary, a beautiful but fleeting configuration in an endless sea of more stable and utterly alien possibilities. This final cosmic destination is known as the Omega Point, a theory proposing that the entire universe is evolving toward a state of ultimate consciousness, a moment of infinite knowledge and existence. It is a vision of our cosmos not ending in fire, ice, or vacuum decay, but achieving a kind of divinity. Physicist Frank Tipler built this idea upon a specific cosmological model, a closed universe that will one day stop expanding and begin to contract under its own gravity. In this great recollapse, the universe would fall back in on itself, heading toward a final singularity, the Big Crunch. But Tipler saw this not as an end but as a culmination. As the cosmos contracts, the energy available for computation and information processing would increase dramatically. Intelligent life, or more likely its vastly advanced descendants, would harness this escalating power. They would use it to run simulations, process information, and expand consciousness on a scale we cannot fathom, all in a desperate race against the encroaching end. The goal would be to outpace the collapse itself, processing information faster and faster as space shrinks, creating a feedback loop of exponentially growing consciousness. At the very final instant, at the point of the singularity itself, this process would achieve an asymptotic state of infinite information and infinite awareness. The universe would, in its last moment, become omniscient and omnipotent, a being that knows everything that can be known and has experienced every possible existence. This is the Omega Point, the universe waking up to itself just before the curtain falls. This theory is intimately tied to the final anthropic principle, which states that intelligent information processing must come into existence in the universe, and once it comes into existence, it will never die out. The Omega Point is the ultimate fulfillment of this principle. It suggests that the universe's very laws are fine-tuned not just for the emergence of life, but for its ultimate ascension into a final, necessary state of cosmic self-awareness. The universe had to have the parameters it does so that it could one day give birth to a mind that would eventually become its own God. The implications are staggering. In its final moments of infinite computation, this cosmic consciousness could simulate every possible reality, every life that ever could have been lived, resurrecting every being that ever existed in a perfect simulation. From our perspective, it would be indistinguishable from an afterlife, a final act of cosmic preservation. While the scientific community largely views the Omega Point as a highly speculative, theological, philosophical argument, it forces a profound question. Is consciousness a random accident, or is it the latent purpose woven into the cosmos from the very first moment of the Big Bang, a seed destined to blossom into the ultimate reality at the end of time? We have journeyed across a landscape of ideas where reality itself is reimagined. From cosmic strings and holographic projections to multiverses and simulated existences, each theory represents a profound attempt to map the unknowable. These are not just flights of fancy, but rigorous and often startling extensions of our best mathematics and observations. They push the limits of what we can conceive, forcing us to confront a cosmos far stranger and more wonderful than we ever anticipated. This exploration reveals something fundamental about our place in the grand scheme. We are tiny beings on a fragile world, yet we dare to decode the architecture of everything. It is a humbling endeavor, one that underscores both our insignificance in the vastness of space and time and the remarkable power of our curiosity. The quest to understand the universe's hidden structures is ultimately a quest to understand ourselves and our connection to the cosmic whole. The stars have always called to us, and now, armed with these incredible possibilities, we have even more reasons to keep looking up. The conversation does not end here. We want to know which of these 30 theories resonated most deeply with you. Was it the holographic principle, the idea of a cyclic cosmos, or the haunting possibility of the simulation hypothesis? Share your favorite in the comments below. Your thoughts fuel this ongoing exploration. If you enjoyed this journey to the edge of understanding, subscribe for more deep dives into the great mysteries of space. Keep questioning, keep wondering, and never stop looking up at the stars.